Dear students, welcome to you. Today we are going to discuss what is the syllabus of BSc Part 2nd Statistics Semester 3 Paper 5. So up to now you have studied 4 papers in BSc Part 1st Semester 1 and Semester 2. In this year we are going to study again 4 papers and 2 practicals. In semester 3 there are 2 papers, paper 5 and paper 6. Paper 5 I am going to cover, and paper 6 Kosti sir, he maybe already started the syllabus. Now we'll see what is syllabus for this semester 5 paper, semester 3 paper 5, and then we'll begin with the actual syllabus. See, in paper number 5 there are again 2 units: discrete distributions, which are defined on infinite sample space. 3 distributions we have to study. One is Poisson distribution, second is geometric distribution, and third is negative binomial distribution. So in the BSc part 1st semester 2nd, in paper number 4 we have studied some of the distributions which were defined on finite sample space, namely 1 point distribution, 2 point distribution, Bernoulli distribution, discrete uniform distribution, binomial distribution, hypergeometric distribution. All these distributions are defined on finite sample space. What do you mean by finite sample space? Number of elements in the sample, they are finite. Now in this paper we have to study some distributions which are defined on countably infinite sample space. That means number of elements in the sample space we can count, but there is one-to-one correspondence with the sample points in the sample space. So 3 distributions we have to study. One is Poisson, second geometric, and third is negative binomial. Then we have to go for continuous univariate distribution, some examples based on that. And second unit we have to study continuous bivariate distribution. This unit very much important as the semester 4 paper is concerned. So all continuous distributions we have to study in the paper 7 in semester 4, and for that beginners, or it is a basic study we have to do in the unit number 2. So what do we mean by continuous bivariate distribution? How to make the transformation of continuous random variables. So these things mainly we have to study in paper number 5. Now this is the syllabus. Only 2 distributions are there, and just will okay, we'll begin with the actual syllabus of this paper number 5. We'll begin with the discrete distribution. Now to study discrete distributions defined on countably infinite sample space, we have to study some terms which are used in studying the discrete distribution dependent on countably infinite sample space. So we are aware with sample space. What do you mean by sample space? It is a set of all distinct possible outcomes of an experiment is called as a sample space. And we know that the sample space is generally denoted by Greek letters script omega, this capital omega, according to the number of elements in the sample space. That means how many elements are there in the sample space. Depending upon that, there are three types of sample spaces. So what are that? So these are respectively, first one, discrete sample space with finite sample points. So this already we have seen in the BSc part first. For example, tossing up a coin, single coin is tossed one time, then we know that there are only two possible outcomes, head and tail. So head is the first sample point, tail is the second sample point. We can count this one, two, like that, and therefore this is the example of finite sample points or a discrete sample space with finite sample points. Second sample space is a discrete sample space with countably infinite sample points. And third one is continuous or uncountably infinite sample space. So we'll see first. Our interest in this topic is a second type of sample space, that is discrete sample space with countably infinite sample points. So what do you mean by that? Countably infinite sample points. It is a set is countably infinite if its elements can be put in one-to-one correspondence with the set of natural numbers. That means we can make the set, or we can make the counts one by one, the set of natural numbers. In other words, we can one can count of all elements in the set in such a way that even though the counting will take forever, we'll get to any particular element in a finite amount of a time. For example, a coin is tossed till it shows head. So see, in example number 1, when we study the discrete sample space with finite sample points, how many sample points are there that is known to you? So tossing a single coin, there are only two sample points, head and tail. If two coins are tossed simultaneously, there are four sample points, H, T, TH and TT. Similarly, if we toss three times a single coin, then there are 2 raised to 3, that is 8 sample points are there. So exact number of sample points are known to us, but in countably infinite sample space, we can put one-to-one correspondence with the set of natural number. So at which stage we have to stop, we don't know. So for example, toss a coin until you get first time head. That means toss a coin, if you get head, you stop there. If you are not getting head, you toss one more time. So in the first toss, you are getting tail, and in second, you are getting head, then you stop there. And you have to continue this procedure. The sample space will be H, TH, TTH, TTTH. Next will be continuous like that. There are 4 times you are getting tail and then you are getting head. So whenever you are getting head, you have to stop there. So how many sample points are there? So we can't count here. But one-to-one correspondence with the set of natural number we can write. Head we can call it is one trial required to get success. Second, TH 2, it will take number 2. How many trials required to get first time head? There is 2, so and so forth. One-to-one correspondence we can put. Now we'll define what is the discrete random variable on countably infinite sample space. So we have a set sample space omega having the countably infinite sample points W1, W2, W3, so on and so forth, be a sample space containing countably infinite sample points corresponding to a random experiment. Now we have to define a real valued function x omega that is based on the sample points defined on domain omega is called a discrete random variable on countably infinite sample space. So mathematically how we can write x omega, that is the sample point from that sample space omega. So we have to go to a real line. So r we have to define there. So for every sample point there is a number based on the real line. Second, same way we can write, suppose w1, w2, w3, these are the sample points on the sample space omega. We give some numbers corresponding to every sample point as x1, x2, x3, which numbers are belongs to the real line r. Shortly we can write as x omega 2 is equal to xi, where omega I, that is every sample point, belongs to the sample space omega. The random variable in this case takes the values x1, x2, x3, so that the range set of x is x1, small x1, small x2, small x3, so on and so forth. Following are some more examples of random variable taking countably infinite numbers. First example, number of trials required to get head. The number of trials. Same example, toss a coin until you get head. So suppose in the first toss you are getting head, so just one trial is required to get head. Suppose in the first trial you are not getting head, that means you are getting tail. So one more time you have to toss that coin. And suppose in the second toss you are getting head, then two trials are required to get first time head. Similarly, x will take value 3 if there are two failures, that is 2 times you are getting tail and then you are getting head. And if this sample space will be continue until you are getting the first time head. Second example, the number of alpha particle emission, range set is 0, 1, 2, 3, so on and so forth. So sometimes there will not be any emission of alpha particle, so that will range set will take value 0. If there is one particle is emission, so it will take value 1, 2, so on and so forth. Next example, the number of trials required to achieve a certain skill in gliding activity. So whenever you are doing some gliding activity, so how many trials are required to achieve a particular skill? So at least one time you have to do that activity. In the first attempt, if you are getting some skill, then it will take value 1. Suppose in the first trial you are not achieving a certain skill, then you have to try for the second time. So 2 trials are required to achieve a certain skill, and so on and so forth. So these are some of the examples in which your sample space taking value countably infinite. Next, as you have studied, what do you mean by probability mass function for countable discrete sample space dependent on finite sample space? In that case, if x is a random variable taking values x1, x2, x3, xn with the probabilities p1, p2, p3, pn, then this function p is said to be a probability mass function if each probability is greater than or equal to 0, and if we add all these probabilities p1, p2, p3, pn, and if it is exactly equal to 1, then we say that that function is a probability mass function. Same case is there. Here the sample space is not finite, it is countable infinite, therefore it will take values, random variable x will take values x1, x2, x3, xn with the probabilities x1, x2, x3, so on and so forth, with the probabilities p1, p2, p3, so on and so forth. Then this function p is said to have a probability mass function if each probability is greater than or equal to 0 for all I, and second, summation of this probability must be equal to 1. Then the function p defined above is called as a probability mass function. Now, second, we have to study the next function is CDF, that is cumulative distribution function. Already this CDF is also we have studied for the finite sample space. So CDF is always denoted by capital F, at which value it is defined, that is denoted by small x, and at suffix we are writing capital X. This is a corresponds to the random variable capital X. The same definition for countable infinite sample space we have to define. So definition is, let x is a discrete random variable taking values x1, x2, x3, so on and so forth with probabilities p1, p2, p3 respectively. Then cumulative distribution function CDF of random variable capital X is denoted by capital F of x at x and is defined as f of x is equal to probability that x less than or equal to small x. So at any value we can define, that is, suppose x takes a value xi, so probability is equal to probability that x less than or equal to xi, that is summation of all probabilities before xi. So x equal to xj, j from 1 to I. That means if it takes value j is equal to 1, probability of x equal to x1 plus probability of x equal to x2 up to probability of x equal to xi. Addition of all such probabilities gives you CDF. Shortly we can write as summation of pj, j from 1 to I from 1 to n. Already we have seen properties of CDF. So generally this question is asked. So write down some important properties of CDF. First property, fx is non-negative. That means since this is a probability always lies between 0 and 1, therefore it is a non-negative. That is, fx is always greater than or equal to 0 for all x belongs to R. Second property is fx is non-decreasing. So it is always increasing or it will become a stagnant at a particular value. So it is non-decreasing. Fx can be defined for any value of x. We can define fx at any value of x, maybe from minus infinity to plus infinity. A range set of fx is always lies between 0 and 1 because fx is a probability, and lower limit is 0, upper limit is 1, both inclusive. So fx always lies between 0 and 1. Distribution function or CDF at minus infinity is 0, f of plus infinity is 1. So these are some of the important properties of CDF. Proof of this also we have studied in the BSc part first, so we are not going into the details. Now some more terms we have to study. One is median of discrete probability distribution. So what is meant by median? Already we know or we are aware with this median. Median is the value which divides the total data, entire data, into two equal parts. So that we call it as a median. Suppose 5 observations are there. If you write this observation in ascending order of magnitude, we have to find out such a value which divides the entire data into two equal parts. Very simple example, if you write the first 5 numbers 1, 2, 3, 4, 5, so they are already in ascending order. So we have to find out such a value which divides the entire data into two equal parts. So 3 is the value which divides the entire data into two equal parts. That 3 is, we call it as a median. Median is the positional average. So in the probability theory, we can find the median by using the definition. If capital X is a discrete random variable with px as a PMF, then m is the median, m is the value. It is the median if two conditions are satisfied. The CDF is greater than or equal to half at m, that is probability of x less than or equal to m is greater than or equal to half. This is the cumulative distribution function at m. So this must be greater than or equal to half, and both conditions must satisfy. Probability of x greater than or equal to m is also greater than or equal to half. If both the conditions are satisfied, then we say that m is the median. Median can be expressed in terms of distribution function. So always here we are not written the distribution function, but this left side, probability of x less than or equal to m, this is CDF at m. So we can write f of m. So how to convert this one? So probability of x less than or equal to m is greater than or equal to half. That is the CDF at m, that is f of m is greater than or equal to half. And the second condition, probability of x greater than or equal to m is greater than or equal to half. So this left side, greater than or equal to m, can be written as 1 minus probability of x less than or equal to m. That is complementary probability. So this must be greater than or equal to half. So this is 1 minus product of x less than or equal to m plus product of x is equal to m. So inequality is not there. We are taking that one. And this can be written in the form of distribution function. So this x less than or equal to m is your f of m plus probability after x equal to m must be greater than or equal to m. So if both the conditions are satisfied, then we call it is m is the median. So m is the median if fx is f of m at x, f of m greater than or equal to half 1 minus f of m plus product of m is greater than or equal to half. Median of a discrete probability distribution is not unique. So for given probability distribution, there may be more than one median. So it is not unique. On the same side, we'll define what is the modal value. Mode is the value for which probability for that value of x is a maximum. So definition we can see x is a discrete random variable with the probability mass function px. If m0 is the mode, if m0 is the maximum of probability of x equal to small x. So see the values of x and see corresponding probabilities. So which is a maximum probability, corresponding value of x is we can call it as a mode. Again, mode may not be unique. If there are two modes, then the distribution is called as bimodal. If in some cases, if there are more than two modes, we can call it as a multimodal. Okay. So we'll see some examples in which how to find out the modal values. Now next part is expectation of discrete random variable. In the BSc part 1 also we have read for the finite sample space how to find out the expected value of x. Here for countable infinite sample space also we can find the expectation of a random variable. Its a definition: x at capital X is a discrete random variable taking countably infinite values x1, x2, x3 and so on and so forth with probabilities p1, p2, p3 and so on and so forth, such that each probability is greater than or equal to 0, and second condition, summation of all these probabilities must be equal to 1. Then the mathematical expectation of a random variable capital X is denoted by capital E of x. See, whenever we are writing expectation of a random variable x must be the capital letter because it is a random variable. E of x is the notation for expected value of random variable capital X, and is defined as E of x is equal to summation of xi pi I from 1 to infinity. See, in the last year the summation was for the finite case, I from 1 to n was there. Now our sample space is countable infinite, so it take many values. So expected value of x is equal to possible values of xi with their respective probabilities, sum of product of this xi and pi, you will get the expected value of x, provided this summation exists. If it is exist, then and then only we can find the expected value of x, otherwise it is not. PMF, sometimes it is better to define PMF of random variable x by px. In that case, expected value of x is summation of x into px. It exists when a summation of absolute value of x px must be finite. So already these theorems with proofs you have studied in the BSc part first. Expected value of a constant is a constant where c is any constant. Expected value of x plus b, that is expectation of change of origin. B is the shift, so in that case it is equal to expected value of x plus b, where b is any constant. Next property, expected value of a into x, where a is any constant, so that is equal to a into expected value of x. That is effect of change of scale on expectation. So there is expectation of ax is equal to a into expected value of x. Now fourth property, we are taking effect of change of origin and scale simultaneously. Expected value of ax plus b. So a into expected value of x plus b, where a and b are any constant. That means expectation of a random variable is affected by change of origin as well as change of scale. Now fifth property is the addition of expectation of addition of two random variables, e of x plus y or e of x minus y is equal to e of x plus y, or if it is minus, then expected value of x minus expected value of y. If x and y are any two different random variables. And sixth property is of independence. If x and y are two independent random variables, then expected value of product of their random variables x and y, that is e of x into y, is equal to e of x into e of y if x and y are independent random variables. So all these proofs we have studied in the first year, and therefore proofs are not expected here. So those who are interested, they can see the last year notes, so you will get the proofs of all these expectation. Okay, in the next period we'll see what do you mean by moments of a random variable. So what do you mean by a raw moment about origin, a raw moment about any arbitrary point? Then what do you mean by central moments? What is the relation between raw moments and central moments? If you know raw moments, then how to find out the central moments? And after obtaining the central moments, we can study the nature of that random variable by obtaining measures of skewness and measures of kurtosis. So what is the nature, whether it is positively skew, negatively skew, or it is symmetric, or in the kurtosis we can say it is whether it is leptokurtic, platokurtic, or mesokurtic. So already we have studied this one in the previous year, even though we have to recall all these moments, skewness and kurtosis, because this is a very important to study the skewness and kurtosis. Okay, today we stop here. Thank you.